Okay, firstly, I'd like to thank the organizer for giving me the opportunity to present this work. Okay, so today I'm going to talk about how to measure the boosted hadronic polarization of boosted hadronic double boson using jet substructure observable or jet substructure method. This work has been done in collaboration with Professor Vikram Rentala of IIT Bombay and Professor William Shefford of Sam Houston State University. This is the first version of the work on which we did some major upgradation, and today I'm going to talk about those upgradations. Okay, so this is the main outline. So let me start by giving the introduction. Okay, so at high energies, longitudinal gauge boson scattering would violate unitarity in the absence of Higgs boson, or if the coupling of the Higgs boson with the gauge boson is not the same as that predicted in the standard model. In either of the cases, this scattering amplitude will grow as energy squared and the unitarity will be violated. Now, to solve this issue, if one introduces a Higgs boson with the same gauge coupling G, then it will result in a diagram like this, whose scattering amplitude will grow as energy squared with a negative sign. So, this will cancel its effect and the unitarity will get restored. Now, there have been many BSM theories as well, which states that there may be some massive Higgs boson present or maybe some massive technohadrons present, which predominantly decays to longitudinally polarized double boson at high energies and may be responsible for the restoration of unitarity. So, it is very much important to look into the vector boson scattering at high energies, specifically longitudinal vector boson scattering at high energies, and hence it is important to measure the polarization. Now, this is what the vector boson scattering looks like in LHC, where W plus and or W minus, this W boson can either decay leptonically or hadronically. Currently, CMS and Atlas has measured the W polarization in its leptonic channel. But we know that the branching ratio of the W decaying to hadrons is about 68%. So, if we were to measure the polarization fraction in the hadronic channel, it would increase our statistical graphs over the polarization fraction. And also, we do not have to think about the neutrinos and the missing energy. We can reconstruct the full kinematics of the final state particle. Henceforth, we look into the hadronic channel of the W boson, rather hadronic decay of the W boson, and try to estimate the polarization of the W boson. Okay, let's look into the parton level angular distribution of the W decay product first. Let's say W plus is decaying to U and D bar in its W rest frame, and this angular distribution will solely depend upon theta star or cos theta star. Now, using helicity conservation principle, we can establish relationship between this decay amplitude and cos theta star for both the polarization state of W boson. And from the distribution here, we could see that the angular distribution for longitudinally polarized W boson is maximum when cos theta star is 0, which indicates the fact that the decay products prefers to align themselves perpendicular to the boost axis. And for transversely polarized W boson, the distribution is maximum when cos theta star is either 1 or minus 1, which indicates the fact that the decay products prefer to align themselves either parallel or antiparallel to the boost axis. Now, from this, we can see that cos theta star is a good polarization discriminator for W boson at its rest frame. Now, what we need is a lab frame observable which can give us a direct inference on this rest frame distribution. So, we move on to how to construct a lab frame observable. So, first let me tell you the distribution of the W decay rate as a function of its decay polar angle, which is given by this equation, where the transversely polarized W boson will follow a distribution like 1 plus cos squared theta, and longitudinal will follow 1 minus cos squared theta. This is normalized as 3/4, this is normalized as 3/2. And these are the polarization fraction which are constrained by this equation, that is Ft plus Fl should be equal to 1. Now, if we had access to the experimental distribution of the W decay at different theta star, then we could fit the distribution to this equation and extract out the Ft and Fl. But we do not have right now. So, okay, so these are all parton level things. Now, at LHC, what we see are all hadron level things. So at hadron level, for a highly energetic W boson, the two jets that are coming out from the W decay, which corresponds to two quarks at proton level, will be highly collimated and will combine to form one single jet, which is called the fat jet, and that would correspond to the W boson. And the two quark jet will be the subjet of that fat jet. Now, how to construct this theta star from this final state particle in order to measure the polarization? Well, one way, that is the way that CMS has tried to do, is to construct the opening angle between two subjects, and this opening angle is related to theta star through this equation. So, but we see that this opening angle is a poor proxy variable. This is the behavior of opening angle as a function of cos theta star, and we could see that this opening angle has very flat values for a large values of cos theta star, and it is even flatter for high boost. So, for a high energetic W boson, if one measures the opening angle and makes some errors, then the error will propagate and will give a large error in the inference of cos theta star. So, what we do is we suggest another alternative proxy variable for cos theta star, which is delta E. So, if we boost the W rest frame to the lab frame, we get a configuration like this, and we say that the energy difference between these two quarks will be a potential polarization discriminator at the lab frame. And this is how we relate the lab frame observable to the rest frame observable. So, if you like from the expected distribution of the from the expected distribution, we can conclude, or rather we can infer, that for longitudinally polarized W boson, there will be equal distribution of energy between the two quarks, and there will be unequal energy distribution between two quarks for transverse modes. So, how to construct this angular distribution, which we call P theta? So, first we identify the W fat jet, then we use n subjectness to identify the two subjects inside that fat jet and reconstruct the energy difference between those two subjects. And we also note down the momentum of W fat jet. So, upon getting the reconstructed energy difference and the momentum of the W in the W lab frame, we take the ratio and construct this proxy variable P theta. So, once we have event by event measurement of P theta, we can make the distribution, fit it to the W decay rate, and extract out the polarization fraction. Okay, so let me show you the performance of a proxy variable, but first we need to construct templates, like templates of how P theta is for purely transversely polarized W boson and purely longitudinally polarized W boson. So, we do a theoretical simulation of this process where PP going to a fictitious particle, where fictitious particle decays to W plus and W minus, and they decays hadronically. This is the flow chart we have followed to construct those two templates. So, we have kept the mass of the fictitious particle to 100 GeV, and we have considered this phi to be scalar when we are generating longitudinal templates, and phi to be pseudoscalar when we are constructing transverse templates. And since we are talking about boosted W boson, we have kept the PT of W between 800 to 1000 GeV. We did showering, Hadronization, then gen clustering in FastJet, and note we didn't do any detector simulation, and we imposed these two criteria to tag the W jet, and then we construct the P theta. Okay, to demonstrate the efficacy of a proxy variable, we have constructed the cos theta distribution in various bins along with the P theta distribution for both the templates. And we can see that the P theta is a good proxy variable for cos theta star less than 0.9 with some spread, which is kind of expected due to subjet misreconstruction or non-perturbative effect. But in the last bin, which is from 0.9 to 1, the proxy variable is not a good one for cos theta star. So, the plausible explanation is that for cos theta star greater than 0.9, at leading order, at parton level, W decay will be in such a manner that one parton will lie along the boost axis and other pattern will lie against the boost axis. And if we go from the rest frame to the lab frame, the pattern that lies opposite to the boost axis will change into a soft wide angle emission that will get removed by jet grooming. That will result in a single prong jet. Now there is a non-zero probability that there could be radiation coming out from that single prong, and it would behave as a double prong jet and would satisfy the cut criteria. So that's why so the angle between those two prongs will be determined by QCD, not by the Hadronic level distribution, and henceforth we get a flat distribution like this in the last beam. So hence we can say that p theta is a good proxy variable for cos theta till 0.9. Okay, so finally we get a 1D template of p theta. This one is for purely longitudinally polarized W boson, and this one is blue one is for purely transversely polarized W boson. We also did simulation for the QCD background, and in principle, if all these three distributions were characteristically different, then we could do a fit and extract out the polarization fraction. But from this figure, we could see that the QCD background distribution is quite similar to that of the transverse distribution. And we found out that this closeness is due to the value of insubjectness cut that we choose. So what we did is, instead of applying both the insubjectness cut and the mass cut, we just applied the mass cut and constructed the distribution between p theta and tau to 1, which is the insubjectness. Okay. So yeah. So this template, so we can fit this template in this expression to extract out this FL, FT and FV. So what we did finally is we applied these 2D templates to extract out the polarization fraction in a VVS scattering at HLLHC. So we did a crude estimation of the number of events expected at HLLHC. We take a current CMS study on VVS, and this is done at 138 femtobarn inverse, and we scaled up to 3000 femtobarn inverse or 3 attobarn inverse, and also we looked into 10 attobarn inverse of data, and these are the events that we found out. And also we have assumed 20% of the signal events to be longitudinally polarized. So longitudinal W is 425 and transverse W is 1739 events for 3 attobarn inverse events, and for 10 attobarn inverse of events, these are the values. Okay, so what we did is we constructed pseudo data by taking the linear combination of these three templates in this ratio and then adding a Poissonian noise to construct the pseudo data. Pseudo data is fitted in this linear combination of the templates to extract out these three parameters by minimizing the chi-square. Now, alternatively, what we did is we switch these parameters to n total, which is the summation of NL, NT, NB, FL, which is the ratio of NL by N total, and FT, which is the ratio of NT by N total. And we did this procedure for 10,000 pseudo data and noted down the average reconstructed values and compared with the truth values. This is for 3 attobarn inverse luminosity, this is for 10 attobarn inverse luminosity. And finally, we found out that, okay, so we can detect the transversely polarized W boson with 30% accuracy at 3 attobarn inverse and 20% accuracy at 10 attobarn inverse. But we cannot detect the longitudinal polarized W boson, as they cannot be distinguished from 0. So what we feel is that if longitudinal W boson polarization is enhanced in a BSM scenario, then this technique could be useful. Otherwise, it helps to measure the W boson polarization in VBS at HLLHC to within 20% error. And these are the summary. That is, we have proposed a new technique which uses just substructure method to construct a proxy variable p theta, which does a better job than the current proxy variable that CMS uses. And yes, this is the result. That's it.
Thank you. Any questions?
So standard way of doing it is to see same sign lepton pairs.
Yes, yes.
So is this method better?
We tried to motivate that we should look for hadronic channel because that have much more statistics.
But the background is also
Right. So that's
unless
kind
we
of,
do this signal to background ratio, etc., maybe it
yeah,
will not sell so much.
yeah, right.
Sure. Provided we can, because the rate is so small for vector Bosons scattering, the QCD. Sure, but still the amount of multi-jet background is always very, very large, extremely large. So in certain corners of phase space, there will be still events from QCD multi which satisfy similar topology. That is the main form.
But their ones are 30%.
Yeah. Anyway, so nice.
So you said, so if it's WW and there are two neutrinos, then how do you, like here it mattered the angle between the WDK products. So in that case, what technique does CMS use to, yeah, if both are lepton, you miss both the neutrinos, so you don't have this information of the WDK completely, right? And that carries some information over this. You can do some information is still there. Okay, thanks.